Hello everybody, my name is Ryan O'Keefe and I'm going to be running through problem 7-8, parts A and B, out of Elements of Chemical Reaction Engineering text, 4th edition. I chose this problem because it uses a non-chemical engineering situation, and we're going to use that to demonstrate the pseudo-steady-state hypothesis. Specifically in this problem, we are modeling a public health crisis, which is very appropriate, and we have these three species: H or healthy people, I or ill people, and D or dead people. And they're all going to interact according to these four equations here. Healthy people can become ill. An ill and a healthy person can become two ill people. An ill person can recover and become healthy, or they might not be so lucky and they might die and become a deceased person. So we're using the pseudo-steady-state hypothesis, as I mentioned, and that's going to tell us that our rate of our intermediaries can be assumed to be 0 over time. In this case, our intermediary actually is our I term. I's are created and then consumed, and then at the end of the day, or in this case, the end of the epidemic or whatever emergency we have going, there should be no more I left. People will either be H, healthy, or D, dead. No more I. So part A is asking us to come up with a death rate, or RD, but to get there, we're going to start off with RI, and we're going to say that everywhere that I is being created, such as these first two terms, are going to be positive. We're creating I. Everywhere it's negative, in these three, it will be negative. We're losing I. 2 is kind of a special case. We're creating 2 while consuming 1, so on the balance, we're just going to say that we're creating 1 and not worry about it too much. So we have positive K1 times the concentration of H. We have positive K2 times the concentration of I and H. We have negative K3 times the concentration of I and negative K4 times the concentration of I, which is what we have going on over here. The rate of death is going to actually be much simpler because it's only in that fourth term there. We have the rate of death is K4 times I, concentration of I. You will notice that it was positive in this term and negative in that term, again, because the negative, we're talking about the consumption of I, we're losing it, versus here, we're talking about the creation of D, so positive. We're going to take that first equation, the RI term, back, and we're going to use the pseudo-steady-state hypothesis, set it all equal to 0. We're going to gather up all the terms that have CI in them, common, and move them all to one side of the equation. And I apologize, this K4CH should actually be K4CI, it's a slight oversight. So that's going to leave us on one side with the concentration of ill people times the quantity here of negative K2, concentration of healthy, plus K3, plus K4, and all that's going to equal K1CH. In our next term, I rearranged, make it a little bit better with the positive terms out front, negative term in the back. But in essence, we just divided that away on both sides, so we get this CI is equal to this nice piece right here. So we're going to go back to our RD term. We have CI hiding there, so we are going to insert our new term, and we're going to have RD is going to equal the original K4 times what was CI is now this, and finally it's going to equal K1, K4 over the sum K3 plus K4 minus K2CH, all that times CH. So that is our rate of death term. Part B, a little bit of a thought experiment. It's going to ask us when will the death rate go critical, and I assume that to mean that the rate of death would explode, it would go towards infinity, it would get so large that we couldn't handle it, and that's essentially going to happen when this denominator here gets very, very small. A number over a very small number goes to infinity, so we're going to say what happens when this denominator goes to 0. So we're going to take that and set that equal to 0. We're going to move any terms away that don't have a CH in them, and then divide away the K2 here to get the concentration of healthy people, when this concentration of healthy people is equal to the rate constants of 3 and 4, both of those divided by rate constant 2. When that happens, we will have essentially Armageddon. Everybody will be dead or dying or soon to die. So hopefully that is not the current situation. But I hope this was helpful to you and helped explain the utility of the pseudo-steady state hypothesis for generating more advanced equations and models based on what were simple equations originally. So I hope you enjoyed, and have a great summer.